So we got a very big evening tonight, and so next slide. So on today's agenda, we got so today is basically an opening night from the Space Institute, and so we got a lot of speakers from the Space Institute. And so to start off with, we'll have a talk from Professor G. I'm not too good at pronouncing his name, but I'll give it a try anyway. Professor Guglielmo Aglietti. I hope that's a good try. Otherwise, we have a number of students, PhD students, Annalisa, Jason, Mikhail, Thomas, and Antonella, who will be giving us a talk. If you click record, actually, that's really cool.
1 second.
Oh, yeah. Carl, could you click the record button?
It's recording.
Oh, okay. Awesome. Oh, should I? Okay, anyway, I just want to point out that the Space Institute is a sponsor of us. They are our super sponsor. We would like to thank them again for sponsoring us. Otherwise, yeah, and in terms of today, so basically, we're going to have a number of talks, and then after each talk, there's going to be a very brief Q&A because we have a lot of talks today, and then after all the talks, then we'll have more Q&A if there are questions. But otherwise, I hope you guys enjoy.
Okay, guys, I hope that you can see the presentation in presentation mode. I'm Professor Guglielmo Aglietti, the director of the Institute. And just say, a few words about the Space Institute. This was created about 3 years ago as a cooperation between the Faculty of Science and the one of Engineering. And the purpose of the Institute is really creation and dissemination of knowledge, that means, research and teaching, to really help the growth of the space sector. And so we are trying to develop, capacity and growth through innovation. So if you look a bit, what there is in the Space Institute, there are various activities that are going on. Some are the more, let's say, academic stuff, again, research and teaching, because we are based within the university. So this is our core sort of activity. But at the same time, we want to be able to actually develop, real technologies, to test these technologies in space. And so we have other areas of the Institute that are really focusing more on the development of hardware, the testing of this hardware, and then running the operations in space using, for example, the Missile Operations Center where you are today. So during this presentation, I will talk to you about more in details about these different areas. But in practice, the key capability of the Space Institute should be really this, or the ability to go from concept of a new piece of hardware, of a new mission, and so on, to the development and the in-orbit demonstration, and all this to try really to help the growth of the sector. And we have technical expertise that cover a lot of different areas, from the CubeSats, nanosatellites, space technologies. In particular, my area is more mechanical systems, structures, but again, there are colleagues that work on material, astrophysics, optical telecommunications, space situational awareness, and so on. As you can see from this diagram, we engage with international organizations, with industry, the space agency. So if we start to unpack a bit what there is in the Space Institute, and there is a mismatch between what there is here and what there is there. Okay, now is, okay. There is a bit of a delay here, but okay, if we start from the academic stuff, when I arrived, again, about 2.5 years ago, I noticed that in New Zealand, there wasn't really a course in any university that was covering space or aerospace, and the sector really wanted to have people with this kind of expertise in order, again, to grow and hire these new staff. So we set up a new course, a new master in aerospace engineering, and then various other educational activities. And again, we started also a lot of research activities. Some were already going on. There were also some activities with the APSS, for example. I'm sure you are aware about those. But again, we started also to develop further space technologies. And in particular, there is a growing research group in space situational awareness. And maybe in one of these sessions in the future, you can have speakers specifically about space situational awareness. And then if we talk about the various areas here, prototype assembly and integration, that's important because, again, when you have your ideas, it's important to actually see if these ideas work in practice. So there is an area of the institute where you actually can go and try these ideas, try to put together your bits and pieces. We have a clean room that is actually just across here, the corridor, where you can start to develop your particular piece of art, your technology. And then once everything has been, is behaving as it should, you have really to go and test it, because for, in our sector, to test, for example, the capability to withstand the launch environment, or the capability to survive once you are in space is crucial. So we have an environmental test facility, which is downstairs. And then again, the Mission Operations Center, because once you have put together your hardware, you are tested, so you are quite sure that it should work, you want actually to have an in-orbit demonstration, and then to use the data. And in order then to run your space mission, you need a room like this, where you can actually control what's going on. This room is then connected to some antennas that can actually communicate with your satellite, so you can send commands, see what the satellite is doing, download the data, and then use the data for various services. I don't know, it could be Earth observation, it could be telecommunication, all these things. And ultimately, so what we want to do is really, we want to work on missions and applications, and what we want to create, our output, is really new people that can go and work in this sector, spin-offs where some of our ideas actually show that they've got good commercial potential, and again, R&D. And so this is all stuff is going to be useful for the space industry. And what ultimately we want to produce is really this economic growth. And one of our main, let's say, body with which we engage is the space agency. As the space agency set, the policy, the strategy, and so on, and we try to work with the agency to then help to deliver this growth in the sector. If we now look at the various bits that I told you before, for example, the educational stuff, the Master of Aerospace Engineering, which is one of our activities, the idea is that this is like a stepping stone for people that maybe have, a generic degree in mechanical engineering or science, and really want to know more about really space, so space things, to then get a job, for example, in the space sector. So part of this master are various courses that you see, for example, listed there. The first 3 courses have been already running for the past year. Now, next year, probably there will be operating the course about satellite operations and communication, and the next one about remote sensing. But so there is a mixture of courses and a project, and the project can be big or small, depending on what the students want to do. And the idea is that these projects are really in collaborations with industry or with other institutions, because students can actually start to cross the bridge between the academic learning and the real applications in industry. So they are a good opportunity for the students actually to put into practice what they have been learning. And then again, once they have done the master, clearly, some students will get jobs in the various companies that are around here in New Zealand or abroad, but there are plenty of opportunities. For example, jobs in academia, in various research institutions, consultancy, and so on. And by the way, besides these courses that you see here, the first 5 that are really spacey, aerospace stuff, the students can also choose a variety of other courses that are things that are relating, but they're not really specific just to space. For example, composite materials or so the whole room is pretty large, 160 square meters. So it's a big room where there are two areas that you see on the side there on the left, and there are one more electronic workshop, the other one is more a mechanical type of workshop for final piece of adjustments. Then there is a main area in the middle where, again, research students, staff do, start to assemble the various pieces of technologies. And then finally, they go in the clean room, which is this one that you see in pink. This is a proper class 7 clean room where you can assemble stuff that is ready for space. We have sized all this stuff in a way that you can easily handle, large CubeSats up to, 60 units, that is 16 units, which is, relatively large. Not too big because, again, we don't want to have to start dealing with, cranes and so on to move things. So for us, an ideal size of CubeSats that we would want to use is something that is more or less the size of a microwave oven. So maybe, 20 kilos, something like that, because we think that's a size that can deliver some useful services, but it's not too big to be handled in a university environment. But again, something has been sized also in the test facility to deal with stuff up to 50 kilos, which would be for a university facility quite a significant size satellite. All modular, so we will see how things go, and so certain areas can be expanded or contracted. Downstairs, there is an environmental test facility. Then maybe again another time we can organize a visit so you can actually see what it is. Then you can see some of the pictures of the equipment. And in this environmental test facility, what you mainly test against is the vibration environment, for example, during launch, and the situation in space. So vacuum, thermal oscillations, because the satellite will be sometime in view of the sun, sometime in view of eclipses. So the main pieces of equipment that are downstairs are really shakers, like these two here. And for example, the one that you see here in this picture is really a state-of-the-art shaker because can shake simultaneously in 3 directions, and so can reproduce very well vibration environment during launch, whereas the normal type of shaker shake only one axis at a time, which is not really what happens during launch. But then again, we have a vacuum chamber, actually thermal vacuum chamber, which is about, again, from the picture that you can see, but it's a bit more than a meter diameter and a meter length, because again, the idea is to be able to fit in something that can be up to 50 kilos, half a meter by half a meter by half a meter. And so with these facilities, you again test and make sure that the various technologies you are working on really don't fall apart due to the vibrations that are during launch. And once they are in space, they can really operate. There are other pieces of equipment downstairs to test, for example, about mechanical shocks and other things that happen during launch. But so again, this is in New Zealand would be the only public, let's say, facility to be able to do this kind of test, because clearly there are companies that have this type of equipment, but they are, let's say, like private companies using these things for their own use. Instead, here we have this equipment that will be used by ourselves for our research activities, our students, but also other little companies around New Zealand, startups, spin-offs, and so on, that they don't have all their facilities, and so they can come here and again utilize all these things to prove their technology clearly without having to buy any of these themselves, because as you can imagine, it's pretty expensive business. And then again, the room where we are now, Mission Operations Center, connected with antennas that are not here on the roof, because that was a significant challenge. So the antennas are in a field that is about 20 kilometers south from where we are now, but they will be connected with the Mission Operations Center, because again, it's important to be able to actually test the technology in space. And this room is so big and has got this particular layout and so on that can be modified, because the idea is that this can also be used for teaching. So part of the courses that we have seen before, that you have seen before, are actually about actually showing students how you really run mission operations. So not just from the book reading the equations for the link budget, but actually students will be able to come here and see in detail how you actually run the operation, how you send the signal to the satellite, what is that you receive back, how you really operate things in reality. And if some of you have looked carefully about these pictures, you'll see that, for example, here there is a separation, which is not in the room at the moment, which is this one here. The idea is that in a few months, we will have to put a separation in this room, but again, it will be something that is transparent and can be open, because sometimes there are things that you do in the Mission Operations Center that are a bit sensitive. So you don't want people in the corridor coming in and looking what you're doing. So this type of partition will be, you can obscure the partition, so creates a safe area where you might want to do some operations and so on, and vice versa. In other moments, you might want to open the whole thing, so students can actually see what's going on, and you can use this for teaching workshops and various things. And so again, clearly you can use this room in a lot of different configurations, groups and so on. The idea was to have a flexible space where you can do different things. Like, for example, today we are doing this in this room, in this formal mission operation center. And the last slide, the master plan. This is the roadmap for the Space Institute. So what we have in mind, I can click the whole thing so you see the whole picture. But the idea at the beginning was to establish the institute for the first couple of years, which is basically now. Clearly, things have been a bit delayed, as you can imagine, by COVID and all the rest. But the first phase was really to establish the facilities, Mission Operation Center, clean room, environmental test facilities, and so on. And these facilities here actually can be grouped together as these national satellite test facilities, because as I said before, is an asset that will be available to the whole country to come here and do these, test their own technologies. And at the same time, as I said, we started the Master of Aerospace Engineering. So we had the first cohort. So now has just started the second cohort. So this whole thing, you should imagine about 5 years span between there and there. So now we are more or less halfway through. There are various activities. Some of them were already going on. For example, like the APSS that you see here. Before I arrived, there were already space activity that was going on. For example, on electric propulsion, on optical communications, on SAR and so on. And my colleagues and myself that joined in the last couple of years added more areas on which we are working. But the idea is that these things will then produce, in-orbit demonstrations. And so we will be able then to develop the technologies and test them in orbit to prove that actually these technologies are working. And so the idea is that after this, all this development and so on, we will have in New Zealand a nice, ecosystem where there are companies, research institutions, all working together, and a nice, flourishing space sector. So this is the plan, and okay, there are various projects I'm working on, but again, I won't talk to you about that because we have the various presentations from the various PhD students. So I will stop here. I don't know if there you want to do questions now or later. Up to you. Shall we go to the next presentation?
Was there some volunteers, or should I just assign a name? You can.
I can take the mask off, you said?
Yes, please. Should be fine.
Hi everyone, I hope you can hear me and see me well. So my name is Antonella. I'm currently almost third year PhD student at the University of Auckland, and I'm working on a magnetic steering system for radio frequency plasma cluster. So basically I'm working with electric propulsion systems, as G mentioned in this presentation before. And my work is done in collaboration with the Australian National University with a laboratory of plasma and fluids. So I'm going to give you a little bit telling you about myself, my background. So originally I'm from Rome, Italy. Then I did my bachelor in aerospace engineering in Manchester, United Kingdom. Then I moved all the way to the North Pole in Sweden, and I did a master in space science and technology. Then I went back to Rome to do an internship with Avio. So it's a company that builds a rocket for the European Space Agency. And finally, I came all the way down here to do my PhD. So, but what are space propulsion? So propulsion systems are basically the subsystem of, for example, a rocket or a spacecraft, and they're used to generate thrust. So one, for example, if you want to launch a rocket into space, then you're going to need a propulsion system. If I want to change the altitude and orbit of a satellite, that is done through propulsion systems. But also if I want to send a spacecraft to another planet or another satellite. There are two main categories of propulsions that you can have for space application. One is a chemical propulsion system. And so basically you're burning fuels, you're having combustion reaction, and that's going to create your thrust. And yeah, the main example is for rockets. Then rockets are launched through chemical propulsion system. The other second big class of propulsion systems are electric propulsions. So basically you're using electric power, and but that can be, for example, electrothermal energy or electromagnetic mechanism, and that is what creates thrust. Yeah. So as I mentioned in my presentation, I'm specifically working with what is called a radio frequency plasma thruster. So I don't know if many of you are familiar with what is a plasma. So basically, a plasma can be considered the fourth state of matter. So you have a solid, you heat it up and you can get a liquid, you heat it up further and you can get a gas. Then if I give more energy to the gas, then what I can have is plasma. So, and you can think of plasma as basically a gas that's composed of ions and free electrons that maintain Gaussian neutrality. So, yeah, examples of plasma can be lightnings. That's an example of partially ionized plasma. All the stars and also our sun are made of plasma, but also we have the upper atmosphere, like the ionosphere, so the upper part of the Earth atmosphere is made of partially ionized plasma. And what causes the beautiful auroras is also plasma interactions. And then here you can see a picture of us having fun in the lab with the plasma. And because of the physics that govern the plasma, like of all the physical mechanisms that govern the plasma, we can use electromagnetic fields to control the behavior of the plasma. And yeah, so what are radio frequency plasma thrusters? So radio frequency plasma thrusters are a new technology of electric propulsion system that has been studied for the last 20 years. And the plasma is produced by electromagnetic mechanism, and it's basically put very simply that heats up a gas, and then you start having collisions between the atoms and electrons, and that is what creates plasma. Yes, and usually you have gases like argon or xenon in laboratory plasma, and sometimes also helium if you have enough money. Then how do you generate, of course, the thrust in a radio frequency plasma thruster? The mechanism is basically the same for our electric propulsion system, and it's basically you are ejecting plasma at very high speed outside your thruster, and that of course creates a force. What's an advantage of working with electric propulsion systems compared to chemical propulsion systems? So they can produce, if I want to move a satellite from point A to point B, I have to produce a certain change in velocity. To produce this certain change of velocity, if I use an electric propulsion system, I'm gonna need less propellant. If I have less propellant, that means all my system is lighter, and my satellite is lighter, so it's also cheaper to launch. One disadvantage is that the thrust value is actually lower. So to go from point A to point B,
Or maybe it's half four, the university has decided that
I think I can, it's okay, you can use the, okay, sorry about that. It's okay, I can look at the screen. I think they can see my
Yeah,
presentation,
that's
right? Yeah.
what's on the.
Okay, so to go from point A to point B is gonna take me longer time. So it is not a problem if I don't have a time constraint on my space mission. But for example, if I have a human mission, then a time constraint is a problem. So yeah. So for now, electric propulsion systems have only been used, have not been used yet on manned mission. And last thing, an advantage of a radio frequency plasma thruster is that it has a very relatively simple design. It doesn't use electrodes, it doesn't even have a neutralizer compared to what is commonly used on electric propulsion, like Hall thrusters. So that means that in theory, they could have a longer lifetime. And now, what is, as I mentioned, my PhD title is what is it? There's a question, I think. We can go through it in the end, maybe.
Yes.
Yeah. So, as I said at the beginning, my PhD is currently focused on magnetic steering of a plasma thruster. So basically, controlling the thrust vector by use of a magnetic field. Up until today, I don't think this is working anymore.
Oh, no, we get rid of it. Click on duplicate. I mean,
No?
can we get?
Maybe the battery. Sorry, guys.
Actually, do you want to answer the question? Or do you want to try answer the
Yes,
question?
yeah. What was the question?
So Miguel asked, do radio frequency plasma thrusters cause any electromagnetic interference with communication?
I mean, it shouldn't be a problem, I think, but yeah, I don't know. Okay, sorry. I don't know. I mean, it could be that maybe the RF antenna could cause some interferences with the electronics around it, but I guess you would shield it, so it shouldn't be a problem in theory. But yeah, I mean, I don't think it's gonna be a problem. Okay, yeah, it works. Okay, so as I was saying, up until today, the thrust vector of a spacecraft has been done by using mechanical system, and that could be like either a gimbal mechanism like on a rocket, or you can have vernier thrusters or reaction wheels. The mechanical system means that you have parts that are usually tend to be pretty heavy, but they also move. So that could potentially add some failure modes to your mission. So this idea is that for the radio frequency plasma thruster, you could, because of the, as I said before, the plasma behavior could be controlled by electromagnetic fields. What you could do is you control the magnetic field to actually control where your plasma beam or your plasma plume is pointing. And so yes, the aim of my PhD is to design and test a magnetic thrust vectoring system to use on plasma propulsion systems. And the basic idea is I have 3 coils that are concentric within my plasma source of thruster. And by varying the current in each coil independently, what I can do is I control where my thrust is pointing. These coils basically produce what is called a magnetic nozzle. So instead of having actual physical nozzle, I have a diverging magnetic field that kind of acts as a physical nozzle. And so, for example, if I have my force pointing actually, I can play with the currents in my coils, change the magnetic field orientation, and boom, change the thrust vector. Now, this is, it hasn't been tested before in this kind of system in 3 dimensions. So it's going to be interesting to see how actually the plasma would respond to such an asymmetric magnetic field. And so how are we approaching the problem? By doing experiments. And this is the setup that we have now in the Department of Physics in a lab. And it's brand new, like a month old probably. And it has, for my PhD, I'm working with 3 main components in all this. So this is the vacuum chamber. So basically, this is where the plasma will expand. And it's a chamber which I'm kind of simulating the space environment. So I'm having a very low vacuum, basically to try have an atmospheric free environment, if you want. Then those are the 3 coils that I will use to try and steer my plasma plume. And if you can see, they have a kind of weird 3-dimensional rotational symmetry alignment. Because then what I want to do is just using these 3 coils to control my plasma in 3 dimensions. And then I'm going to use this, which is the matching box plus an antenna. And this, by feeding it RF power, it's what actually creates the plasma from the gas. And this is a little nice picture of when the plasma is on. And yeah, it looks like a lightsaber, probably. Yeah. And so what I'm up to now, right now I'm trying to have a high density stable plasma in the new experimental setup. Once done, the deed is done, then I can actually start do a preliminary testing of the magnetic transvectoring system. That is followed by actually, then I would like to look more into the plasma generation mechanism in a non-symmetrical magnetic field. And then, of course, I will need to do 3D mappings of the vacuum chamber that I showed you before to actually characterize the plasma and see what are the plasma properties in such a magnetic field system. And finally, I will look into the acceleration mechanisms that happen in a deflecting magnetic nozzle to actually see if all these systems can be used from quantitative applications or not. And yeah, those 2 last points of my future work are probably the biggest part of my PhD. And that's it. Do you guys have any questions? I guess I can.
We might go. Do you guys have any questions right here, or just okay? We might go through the questions later, or
Yeah, sure. And I leave the floor to Anna, to Nina, Tom. I don't know.
yeah,
That's the end of that. There. Okay. Okay, I think that, yeah, it works. Okay.
share it onto the.
Yeah, you have to share also. Yes, okay, here we go. Okay, So, hello everybody, I'm Annalisa and I'm a PhD student here at the Space Institute. And today I'm going to show you in a few slides what my project is about and what I'm currently working on. Basically, from the title itself, you can easily get what is the field of my research, which is deployable structures. And in particular, I'm trying to develop a nanosatellite concept of a deployable antenna, which is supposed to be implemented with a synthetic aperture radar. So, which is the main topic of my research? Basically dealing with deployable structures that are commonly used for small satellite applications. And in particular, trying to find out which deployable structures and which deployable mechanism can be used to store and fold a large space instrumentation that needs to be folded compactly during launch and then to be deployed in space once in orbit. In my case, my large space instrumentation is a deployable antenna with this dimension size, so 4 meter length and 0.8 meter width, that aims to be implemented with the SAR technology that so far has been just implemented mostly in a large and heavy and costly satellite. And that aims to be implemented with my project in a CubeSat satellite, which is the smallest category of satellites. We hope, of course, to do so with the simple deployment mechanism involved. Which can be the scientific objective. It could be the maritime surveillance in the extended territorial waters of New Zealand. So, for example, the detecting of illegal shipping, or long-term measurement of Earth deformation. So, basically, there are a lot of considerations that should be done when dealing with a new project. For example, a PhD project, and I just here sum up which can be the most critical challenges of my project, and trying to find out and try to help myself in focusing on which could be the possible points of innovation, points of novelty, because of course, as you can imagine, most of research has already been done, and so your work should be unique and should be a point of full of points of novelty. And so here there's a list that I'm trying to explore step by step. The first is, of course, the required trade-off between the minimum achievable size of the stowed antenna while maximizing the SAR performance. Following, it's the requirement to minimize the mechanical complexity of our system in order to avoid low reliability, but also to reduce as much as possible the number of components. Another important step would be the material selection for this antenna structure. So the material choice is very important because the material should satisfy the mechanical requirements, but also it should reduce the electrical losses for the radio frequency system. So basically, the antenna should work properly from an electronic point of view. And of course, the trade-off between the flexibility and the stiffness of this structure, because the structure should be flexible enough to be easily folded in a very small volume during launch, but also stiff enough to be deployed, of course, and to be tensioned once in orbit. So a few months ago, I started my second year of PhD. So during the first year, I practically conducted an extensive literature review on which are the most common use deployable antennas implemented with SAR. And then I set up a trade-off study in order to evaluate which of these deployable antennas can be suitable for a CubeSat application. So most of these antenna technologies are used for a very large satellite. And now what we are trying to do is just trying to find out which technology can be suitable also for a CubeSat application. So lately we suggest, me and other guys at the Space Institute suggest some preliminary design concept, and now I'm working on the antenna design process, so doing some analytical calculation and FEM modeling. So I've reported here some of the most common used deployable antennas, which have been used for large satellite, but as you can see here, also for small satellite, and we are in the micro satellite category, so at least 100 kilos, the reflector array technology here. In the reflector array, we can see that the reflector is positioned at a certain distance from the antenna so that it can be properly illuminated. Then here the parabolic mesh reflector that probably is the most common, and as we can imagine of an antenna, is the referring design configuration, but of course this involves a very high mechanical complexity and is not so suitable for a SAR application. In here, most recently, also membrane antennas, very thin layers of membranes, one over the other, have been investigated in order to be implemented with electronics and in order to gain, as you can imagine, very flexible materials that can allow for a very high packaging efficiency. So starting from this technology, I set up a trade-off study where basically we define some system design parameters there, and we set up a trade-off study based on a smart process where first we identify the most critical criteria of assessment and the relative weighting factor in respect to all of these 4 technologies. And what we achieve after a very huge group assessment and lots of workshop session, a big decision matrix to identify which are the most suitable technologies that can be suitable again for a CubeSat application. We also conduct a sensitivity analysis with basically we assess and evaluate, also verify the robustness of our results. So the baseline concept that we achieve is a folded panel reflector array, which is one that can be resembled these, and the second one is the membrane reflector array, both with our reflector array technology. So here we suggest 2 deployment mechanisms for the folded panel and the membrane reflector array. In both you can see that there's the bus here of the satellite, which is basically the same, and the reflector is supposed to be housed in a separate section in order to be deployed through deployable structures, deployable boom, telescopic booms at a certain distance to enable a proper reflection of the signal to the antenna. In the folded panel reflector array, we trade off a certain number, the number of folding with the final stored volume. Why? Because we need to get a solution that can be a balance between the number of folding and the final stored volume. Actually, you can imagine that if we increase the number of folding, we can achieve a lower stored volume, but at the cost of very higher complexity. So the final solution is a 1 horizontal fold and 8 vertical folds, with which we can fold the panels in a Z, like this, in a Z folding method until the final very compact configuration. In this case, I suggest a splitting of the antenna width into 3 strips that can be rolled and open like you can imagine a parchment opening system. And this can help gaining a lot of high packaging. As you can imagine, that each pairs of roll can be open and closed and then fold against each other again with this typically Z-folded method. More recently, I swapped to another deployable superstructure, which is the coiled tape spring. Tape spring are very common use among small satellite application, and basically they are used as deployable booms that can support and tension and enable the deployment of very large numbers of space applications, such as these CubeSat diffraction telescope. These booms is the tape spring that has a 1 meter length, but very small dimension in thickness and width. They have a very high properties of stability. They can stay rolled, and also they have a very rigid configuration when fully deployed. What I'm trying to do is not to use the deployable tape spring as a superstructure, but use the tape spring as the structure. So I'm trying to build an antenna that has the shape of a tape spring. So that all the characteristic and the advantages that we can take from a tape spring can be used for the antenna. In here, I've reported the first attempt in doing so. In this case, it's a 3.5 and 0.3 dimension size, which is almost the one that we want to achieve. In this case, a solar panel structure. What I'm currently working on is the building of a parametric study. Because I have a very few system design parameters at the moment, so I'm trying to find out which is the optimal solution, which could be the optimal solution. So I identify some critical design variables. As you can imagine, for example, this curvature is very important to gain stiffness or flexibility. So I'm trying to vary in different curvature and the different thickness of the tape spring, so this huge antenna, and also different material types. As I mentioned before, the material selection is very important, and so it's a very crucial step. And I'm trying to vary all these variables in order, and also you said here some glass fiber, carbon fiber, composite, so on, and trying to find out which is the optimum, conducting some structural analysis and trying to evaluate which are the natural frequency, the first 1 and 2 natural frequency of the structure, as you can see above some examples. Why? Because I just want to identify which configuration is the most stiff. And so once the antenna is fully deployed, it can ensure me that it stays there. Okay. So this is the last slide, and then I've done. What can be the potential points and future work? Of course, once I've define which is the material, which is the design configuration, I can move towards the deployment process, starting from finding which is the minimum radius of coiling without incurring in failure of the material, so cracking and micro-buckling and every kind of failure that you can imagine. Then I will try to evaluate the bending and stretching energy of the coiled tape spring in order to evaluate again what is the requirement deployment or that we need to deploy the antenna. This antenna aims to be deployed by itself, just thanks to the stored energy that is stored again in the coil configuration, and then they can be released once. I reported this example, which is drag sail coil configuration here. There's a latch that keep the drag sail in that case closed and in that position for during launch, and then after once in space, of course, it can be released by itself. This could be, with these techniques, we could encourage in some high velocity deployment process that we can also consider to control, accounting for the viscoelastic properties of the material. So thank you. I hope it was interesting enough, and if you have any questions.
Are there any immediate questions or?
I think so.
Okay, all right, we'll move on then.
Yeah, sure.
Thank you.
Okay, cool. Good evening, everyone. My name is Thomas, and I'll be having a bit of a chat about my research into soft suspension reaction wheel assemblies to minimize spacecraft vibration. Cool. So these are just a couple of the points I'll cover, a bit of an introduction, an overview of the state of the art, some current problems and gaps, my research methodology into that. And then for every PhD, the contribution to the state of the art and current stages of that before concluding. Okay, so just a bit of a background. Reaction wheel assemblies operate on spacecraft as attitude control devices. So they're a really easy and efficient way to point your spacecraft in the correct direction without having to use precious fuel. When they operate, they can cause detrimental effects to payloads and other sensitive equipment on board. So you can see the source here being our reaction wheel assembly. As it operates, it has an interface to the spacecraft structure that transmits through the spacecraft structure, usually through another interface into a receiver, which can be one of these sensitive payloads on board. And a good example of this is the image down the bottom here. You can see that degradation of the photograph that's taken using an imaging satellite. From right to left, you have a nice straight road, which is what it looks like in real life, and then you get a really weird curvy road afterwards, and that's because of that jitter. Oops, wrong way. Okay, and then just a bit of a background on the current state of the art. So the earliest research was into NASA's Large Space Telescope, later known as the Hubble Space Telescope. And there's a really good literature review that Dennehy completed in 2019, which really covers all the modeling, the disturbance modeling of reaction wheel assemblies. The main kind of takeaway from the research up to date is there's been an excessive amount of research into fixed reaction wheel assemblies. However, the soft suspension reaction wheel assembly has some research gaps, which I'll cover now. So a couple of the gaps at the moment are the bearings inside the motors that drive the reaction wheel assemblies. These are quite sensitive, and during the launch environment, these experience these high static and shock loads, which can be hundreds of G or even hundreds of meters a second, that can detrimentally affect and detrimentally break these bearings or damage these bearings, which is one of the causes of these vibrations in orbit. The second problem that I'll be looking into is characterizing the effect of introducing a soft suspension system into the reaction wheel assembly and trying to minimize these unwanted vibrations. And the third one is experimentally investigating what kind of happens when the reaction wheel axes are not fixed with respect to the spacecraft body. I think we have a master's student covering the mathematical side of that at the moment. looking into it. So our initial research was a design optimization, so similar parametric studies of reaction wheels in FEM. So looking at various parameters such as the thickness of the web here, kind of the height of the rotating mass, the diameter, and what effect this has on the vibrations and on the modes that the wheel will experience, those resonant modes. And then we wanted to experimentally investigate the actual shock loads that are experienced by creating this structure here that has 3 layers that you might be able to see in the photo. So in the middle is a layer of perspex, and inside this has quite a complicated structure that feeds the air. So the airflow comes through these blue tubes. There's a series of channels underneath this top plate, this top frame plate, that then produces an air cushion underneath that central mass and also on the sides. So it essentially floats the mass. And then that whole structure is bolted onto the shaker here, you can see. And then the vibration, like a sinusoid, is placed, well, it experiences a sinusoid. And the accelerometers then measure the accelerations that they experience. A lot of the other modeling that has been done is the FEA and some more of the simplification for the design optimization here. So a lot of the complex geometry here can be simplified, and then you can run pretty detailed optimization studies to find kind of what your best size is given constraints such as like volume or height or radius, outer radius. And then just the mathematical modeling is a common approach that's been used a lot, and even outlined a lot in that Dennehy paper as well. So the design optimization, our primary goals were to maximize momentum capacity, minimize reaction wheel settling mass, and minimize motive bearing loads. So the way we did this was, as I said, parameterizing the reaction wheel into just important components. In here, it's the height and the outer radius of the case. And all of these other components that you can see here end up being related to those. And then what you can do is you can find an optimal external radius increase while also minimizing that mass, which kind of sits about here, somewhere maybe 14 millimeters change in that. So that's an increase of 14 millimeters to find that optimum. So in January it would have been, colleagues of mine, Dr. Vladimir Yotov and Matija, another PhD student, we submitted a paper to the SciTech conference, just essentially covering what I'm talking to you about today. Vlad focused a lot on a mathematical model to visualize the 6 degree of freedom and identify where and when those impacts are occurring. Matija focused a lot more on the finite element analysis, and then I looked at the experimental side. Next slide. All right, and this was my experiment again. So as I explained before, there's an air cushion underneath, so that allows us to ignore frictional effects when we're looking at the impacts that are produced, and we want to initially locate those resonance or impact points for various gap sizes. So the gap between the end of this impactor here and this one here, so this gap between the impactor in the middle and the frame can vary depending on the size of the impactor that's placed in the middle there. And then after we've identified those interesting points, we then increase the sampling rate around those frequencies and around those impacts to get a good idea about exactly what's going on and the exact dynamics in that interaction. And each of these parts are essentially representing a reaction wheel in one dimension. So that central mass is similar to, for example, our wheel at the top. The outer frame is representative of the frame again. And then we have springs introduced that you can't really see, but they contact the center there and also contacted the frame, and these represent that soft suspension system. So some preliminary results that we've got, you can see as a uniform applied sinusoid here, I think it's 25 hertz or something around that. And then you can see the build up initially, some small build up here, and then you can see the really high accelerations that are experienced by that internal impacting block. You can see those and you can identify those impacts that are occurring. And then following up from that, the next step is to really zoom in on those and increase the sampling rate so that we can get an even better idea about what's going on. Okay, so these are that's the 1D experimental impact dynamics experiment is part of the contribution to the state of the art. We're also planning on extending that, so we'll build it into 2D and 3D impact dynamics in the future, and we have a couple of other experiments that are being planned at the moment. So one is just a spring stiffness verification. So when we do our CAD model, when we do our FEA modeling, we can then say, okay, this is what we're representing our spring stiffness K as. Let's do this experiment and verify, okay, what we're actually putting into the FEA model is what we're seeing in reality. And then also quite a basic setup, but a really useful experiment to characterize lateral loads inside the motor. So a simple motor with a flywheel is run up from 0 to 5,000 RPM, and the acceleration and noise signature is acquired. We then hang a mass laterally off that, so straight down, and the shaft of the motor will experience a lateral load. Then what we can do is we can take that lateral load off, run the motor again, see if we can find a difference in that acoustic signature, and that can give us an indication on whether or not there is some bearing damage. Yeah, so just to summarize, the main work that I've been doing for my PhD over the last almost 2 years is an optimization. I submitted a conference paper in collaboration with other researchers, and a lot of experimental work is ongoing at the moment. And I am possibly one of the PhD students that has an industry partner as well, which is a possibility for many students, or for some students, that you can, go in to your PhD and doing your PhD, or you can have industry partners, as G mentioned earlier in his presentation, that can, assist. Yeah, and to conclude, reaction wheel assemblies in operation can cause these detrimental vibrations. Incorporating soft suspension system can help us minimize those vibrations. There's a few experiments going on at the moment in collaboration with other researchers to identify some of these launch environment impacts, and more investigations are planned to look at bearing loads and 2D and 3D impact dynamics. Cool. Some references, and I think that's all from me.
Are there any immediate questions? I don't know. Cool. Okay, no worries. We'll go to the next one.
All right, hi everyone. I'm Mikhail Sayat. So before I did my PhD, I was actually an undergrad here at the University of Auckland in mechatronics and physics. I really love space, but as Jean mentioned, there wasn't really like much going on academically back then. So I kind of ventured outwards. So I went to Poland, did some astronomical research there, went to Thailand in the space agency to develop a satellite tracker, and in the Australian National University to do a high altitude telescope. And quite recently, actually, I took 2 months off my PhD, the last 2 months, to pursue a virtual internship at NASA JPL. But I'm here now, back here to my second year. And my PhD topic is on low Earth orbit, optical ground station, Gaussian modulated, continuous variable quantum key distribution. Long title, I know, but in layman terms, it's basically data exchange or a secret key exchange between a satellite in low Earth orbit to a receiver on Earth in an optical ground station for encoding and decoding future messages. And this is also in collaboration with the Australian National University. Right. So currently what's at play in the background is that Australia and New Zealand are planning to create the Australasian Optical Communications Ground Station Network. And this has many applications, both optically and in the quantum realm. Many partners, and as you can see at the bottom over here, has site diversity, 3 nodes in Australia, 1 in New Zealand. And this is basically where my PhD came out of. As part of this, tomorrow at 9 a.m., I have a flight to the Australian National University, and I'll be staying there for 12 months to work with their quantum optics and quantum information groups. But most importantly, I get to work on their protocol, this Gaussian modulated CVQKD protocol, or as I'll refer from now on, GMCVQKD. So let's look at the background. What's the actual problem? So we're in the new modern space age now. We're sending a lot of satellites into space, and our previous method of communicating radio frequency is becoming very, very crowded, and it's acting as a bottleneck when exchanging information from space down to Earth. A solution to this is optical communications, free space optical communications, by going away from the radio frequency spectrum into ultraviolet, visible, and infrared. And this promises greater frequencies compared to radio frequencies. And to secure this, there's this thing called quantum key distribution that uses quantum mechanics and offers unconditional security, which basically means it's unhackable. So we can see the progression over here on the figure from the previous security being classical, using large prime numbers to factor things and make it secure, and now we're going inherently to quantum. So as I previously mentioned, continuous variable QKD, this is the method of quantum key distribution I'm looking at. So there's the wave particle duality of light, where light can act both as a wave and a particle. This one uses the wave nature of it and encodes keys in what we call quadratures. and that is the amplitude of a laser and its phase. Right now, there's only been one development outside the laboratory, and that's 460 meters terrestrially between a transmitter and receiver in this protocol. However, it's got lots of really good features. One, it's really cheap. It's readily available, and it's more compatible with optical communications. And it also operates at safe wavelengths. So we can see here on this graph the optical phase space, and that represents the quadratures that it operates on. So this is the overall architecture between a CVQKD satellite and downlinking it to an optical ground station. However, for the purposes of my 3-year PhD, I've simplified it to this, where we start off with a laser ground state, we modulate it where we encode certain bits to make the key. It travels through the atmosphere, gets noise injected into it. There's a potential eavesdropper, which we will explore later. And then it gets received on a optical ground station, decoded, processed, and yeah, it's detected through a heterodyne detector. I should also let you know that because I am in a 3-year PhD, the timeline to have an operational GMCVQKD protocol satellite is outside the scope. So I will look into high altitude platforms that act as the low Earth orbit satellite. So in that case, my first research aim was to do dynamic modeling of this scenario, and then we will go into experimental stuff first in the lab, which will be in ANU because they have the protocol there. And then we're going to go outside into the field, have significant distance between it, like the 460 meters. And then what we're going to do is have relative motion in between it to simulate to represent a optical ground station and satellite where a satellite passes over it. And then after that, it's just basic analysis and comparing it to other QKD protocols. So what have I done so far in my first year? I developed MATLAB models, which is really cool, of the scenario. So the first model was of the scope of this. So each compartment was modeled for, and the transmission of what we call Gaussian modulated coherent states. And we'll see that later on in the results of that, which is really cool because I did say that there is unconditional security here. I've also modeled this overall kind of architecture. We have a satellite, the optical ground station, and relative to everything on Earth to calculate the total secret key rate. So I don't know, there's lots of complaints around saying that, you know, we all learn trigonometry, but we actually never use it. Well, ta-da, I use trigonometry here. So yes, and an abstract being submitted to a conference for this later on. And yeah, that's to calculate the secret key rate, which is how fast the key gets exchanged between two parties. And with that, we take into account of geometric losses due to the hardware and the optics in the satellite and the optical ground station. We also take in atmospheric losses because when the laser propagates through the atmosphere from the satellite down to Earth, it will have losses due to aerosols and atmospheric turbulence. And I also modeled the dynamic link distance, which changes because, well, the distance between the satellite and the optical ground station changes as well. It's also been said that, based on literature, 95% of detrimental effects on the laser is confined to the first 20 kilometers of the atmosphere. So then the effective atmosphere length changes as well as in a satellite pass. And did some analysis as well on the Doppler shift due to the relative motion, because there will be a frequency shift and the wavelength shift as well. Right, so the transmission of the GMCS, the Gaussian modulated coherent state, that's the basic skeleton of what was coded. What would happen is we would start off on the optical phase space here. We would have a coherent state at ground at 0, 0. So 0 phase, 0 amplitude relative to something. And then we would randomly modulate the phase and amplitude, and that will go into any one of these quadrants. So then what we can say is, let's say that positive X, or any positive axis encodes a 0, and any negative part encodes a 1. That right there encodes a 0, 0 in binary bits. And we send multiple in a series of these to the optical ground station to create the key. Based on the parameters that I played around with, without an eavesdropper, we can see that there were around 450 measurable bits out of a total 1,000 concerning atmospheric noise. And bit flips is significantly lower without an eavesdropper. So bit flip is we send a 1, but we measure a 0. That's wrong. And that's really bad. However, with an eavesdropper, what we see is the total number of measurable bits significantly decreases and the number of bit flips increases, which is really bad. And then because there's a change in this, we can detect that there's an eavesdropper. And once an eavesdropper is detected, we can then terminate all communications and no one can hack us. And this is where the unconditional security of QKD and quantum communications come in. We can see that closer here. It's actually governed by Heisenberg's uncertainty principle, where the variance of the amplitude and the phase is dictated by that equation, the uncertainty principle. So say, for example, we have no eavesdropper. We start off with something in the ground state. We modulate the amplitude and phase, so it goes away from 0, 0. And due to atmospheric and detection noise at the receiver, it becomes this. So bigger variance because of the noise. However, with the eavesdropper there, again, we start off with 0, 0, we modulate it, and then let's say over here, the eavesdropper measures the amplitude with very small variance, so high accuracy. Based on that equation, what it would mean that is in the other quadrature, there'll be more variance, and that would lead to more noisy bits and more bit flips and more unmeasurable bits. And that leads to the graph before, and then we can detect a eavesdropper. Vice versa in the phase quadrature when it's measured. So I also calculated the secret key rate, and based on the model that I've developed, all low Earth orbits produce a positive secret key rate, which is really good, which means it's feasible for low Earth orbit satellites. I've also looked at the visibility parameter, which measures how clear the atmosphere is. And what we can see is that at very low visibilities, it goes down, and vice versa. The discontinuity over there in the center figure is due to the piecewise function that's used to model this. And conversely, with the elevation angle, which is the angle between the satellite and the optical ground station, it produces this profile for the secret key rate. One really interesting result is that at below 10 degrees, we produce a key rate of 0, which means that you should not operate this protocol below or around 10 degrees. And that's because it goes through much atmosphere, it gets degraded, and the signal attenuates, and you can't get any information out of it. And then analyzing the Doppler shift, I use gpredict, a software, like an amateur radio software, to track LEO satellites. And these are the profiles that I've gotten based on the models I've developed. And when I plug in the elevation angles for the changes in wavelength due to the relative motion. What we can see is there's actually negligible wavelength change, where the central wavelength used for this was 1550 nanometers. And that it's actually the elevation angle that causes this change in the secret key rate, because that was what I plugged into the model for each wavelength used. So once I touch down in ANU, Australian National University, the immediate thing that I'll be doing is benchtop tests in the laboratory and kind of just gaining experience of the protocol that they have there. And once that's been done, we plan to go around Canberra and conduct these horizontal tests where there's significant distance between a stationary transmitter and receiver using the GMCVQKD protocol. And hopefully, with all things go well, we can conduct relative motion tests, not with a satellite, but with a substitute. And right now we're looking to operate it between an optical ground station, either in New Zealand or in New Zealand or Australia, and between something like the Dawn Aerospace Aurora Mark II, or the Kia Atmos, or even UAVs or balloons. And that'll probably happen in the later stages of my PhD. And yeah, just some analysis to compare it to other QKE protocols. Thank you.
Okay. Are there any immediate questions for Mikhail? I don't think. Okay. We'll head. Huh? Yeah. So we'll now head on to our final speaker.
So I need to share my screen.
Yes, please.
Hover over the top right, and then click on the green pop-up.
Okay, so I realize we're a bit overshooting, so I'll try and make this a quick presentation. So as you can tell from the first slide, I've actually finished my PhD. I finished back in August last year. So I'll just give you a really quick overview of what I was doing during my PhD and some of the things you might be able to get involved with in the Space Institute. So my PhD centered around deployable structures and Earth observation. So Earth observation is an important commodity in agricultural sectors, defence, monitoring of natural disasters, and all kinds of research. So we saw a recent example of this with the Tonga volcanic eruption, where for a couple of days all we could get was sort of satellite imagery and imagery from the air. And in terms of the commercial side of things, SSTL have shown that you can get very high quality images from satellites. And this is an example from the Carbonite 2 satellite. So it's an image of Dubai Airport, and you can clearly see and make out, you know, the airplanes, the runway, and the individual buildings, and that sort of thing. So we have shown that it's possible to capture high quality images from spacecraft using fixed barrel telescopes. But one of the remaining challenges that we have is the temporal resolution, or the revisit time, so the time to get back to the same point to take a new image. So the simple solution to that is a constellation of satellites, which is essentially more satellites in the same orbit, kind of offset from each other. Now, with the current fixed barrel images, this is a costly solution because they take up a lot of space in the launch vehicle. So, and because the telescopes are mainly empty space, what people are now suggesting is maybe for launch, we can squash this whole telescope down. So we move the secondary mirror, in this case, down towards the primary mirror. And then we have a smaller volume for launch. And then when we're in space, we can deploy to our focal length, we can take the images. So very simply, by having more telescopes that are smaller, we can stack them in launches and we can save launch costs.
Sorry, there's a problem with the.
Oh, is it?
I wasn't sure.
Okay. I think the laptop's a bit slow, so it doesn't have to. Quick.
It's basically, that's what's showing.
So we're good?
Try moving slides.
No, I think you have to change the screen that you're sharing. If you go,
Maybe we,
that you share.
yeah, maybe we won't do the, what do you call it? Like, just don't click the slide. Yeah, I saw. Right. I was thinking about leaving it like that if it doesn't. Yeah, it might be better to leave it without expanding the screen.
No, but you have to share the different window. You have to share the window where the presentation opens. But,
Okay, it's working.
Working?
Yeah,
You sure?
it looks like this.
Yeah. Okay. So where was I? Yeah, so we can make these telescopes deployable and we can save on launch costs. Going back to the Carbonite 2 example, SSGL were estimating they could save £17 million by having 6 of these Carbonite 2 satellites going from 3 individual launches. So that would be 2 telescopes per launch. So a deployable telescope is great because we can save money and we also don't have to keep the alignment during launch, but then we have some additional challenges that we have to solve. So we have to make sure we can accurately align once we're in orbit. We have to be able to reliably deploy. We need to make sure it's going to get there. And we also need to ensure that the stiffness of the structure is sufficient. So as Tom was touching on before, you can get onboard micro vibrations caused from reaction wheels and cooling pumps, and they act as a base input, like an acceleration input to our structure. And then the optical elements can be distorted and we can end up with the wavy images, which we want to avoid. So the focus of my PhD was to assess a deployment method and assess it for its stiffness. So the deployment method that I chose was tape springs. So these have been used extensively in the space industry. And I'm showing sort of 4 examples of deploys here, so the Annalisa touched on this as well. So they resemble a carpenter's tape measure, but they're in this case made from carbon fiber, which is very thermally stable. I also chose tape springs because they've got minimal moving parts. You just need a deployment drum. They're incredibly compact when you fold them up. So I've only got a short length here, but you can imagine, you know, a 2 meter length coiling to something that's, you know, a few centimeters in diameter. And they're also self-locking. So once they've been deployed, they're very stiff. So they form a nice beam element. And during my PhD, I developed this kind of breadboard model. So this is 6 tape springs that would be located radially around a primary mirror. And this is my kind of secondary mirror on top. So this is kind of half deployed and fully extended configuration. So this is for something like a CubeSat, something like 20 centimeters by 20 centimeters footprint, something like that. So the stiffness of tape springs are driven by 3 factors. You've got the material properties, the geometry, and the boundary conditions. So the focus of my PhD was the boundary conditions. And broadly speaking, there are two types. You've got partially restrained and clamped. So the partially restrained allows you to have a compact coil. So that is, the tape spring folds nicely into a cylinder. But the problem then is it's not very stiff because you've only partially restrained it. The alternative is to clamp the root condition to get a nice stiff root condition. But then the problem is when you come to coil it, you end up with these creases in the tape spring if you try and fold it and coil it too much. You can see in this example that the tape spring is actually broken. So there's that trade-off between the two different methods. So I used experimental methods and the finite element method to investigate this stiffness, and I suggest 3 simple improvements without additional supporting structure that you can make to this partially restrained root condition. So very quickly, you can add additional plies to the root. In the extreme cases of deformation, you can see that the tape spring kind of flares out as you apply a load to it. So by adding unidirectional plies in the Y direction, you can resist this flaring out and this deformation. You can simply increase the region that you're clamping, and you can increase the root length. So that's the material you have of the tape spring behind the bolt connection. So my PhD was quite practical. So you've already seen the breadboard model that I designed and built before. I also manufactured all of these tape strings myself, so there was a lot of composite design work in this. So starting off with the dry fiber braids and the resin films, you lay these all up, and then you apply your consolidation pressure and temperature, and you create the cured tape spring. I also worked a little bit with glass fiber, polypropylene as well, but carbon fiber is the material of choice because of the thermal stability. So having established a good understanding of the sort of static stiffness, I then focused on what happens to the dynamics of these tape springs, again looking at the root condition. So up here I'm showing the first 3 modes of the tape spring with the clamped configuration. First mode 40 Hertz, second mode 108 Hertz, and then moving down here you've got the drum deployed partially restrained root condition. And you can see there's a significant drop in the bending mode. So you've gone from 108 down to 6, and you've gone from 40 Hertz twisting mode down to 12. That just shows you the step down in stiffness you get just from the root condition, which of course is very important for a cantilever structure. So I validated my finite element simulations with experiments, as you should. So this is my experimental setup with my tape spring and a laser pointed at it to measure the distance. So what you do simply is just apply an impulse to the structure, you record your time history. You can then do an FFT to work out what your frequency response is. And in this case, my experimental result matched exactly with the bending mode. And I'll qualify that by saying that this was for an isotropic material. The anisotropic materials are a bit more difficult to predict. So during your PhD, you're going to have a lot of opportunities at the Space Institute to work on other projects, like I did back in the UK, which is where I've come from. So I got involved with this deployable optics project, which is a deployable telescope we developed with SSTL. So it's very simple 3 concentric barrels, carbon fiber barrels that are deployed using a sort of large ring gear and then a series of smaller gears and lead screws. We designed and built that, and then we did some structural testing on it. So this is very, very quickly some results from a science survey. So you're characterizing the structure. So you're looking at sort of the first natural frequency, that sort of thing. So in this case, we're about 95 Hertz. Target was 100, so we're pretty much almost there. And then we also conducted some deployment repeatability experiments, and the column you're interested here really is the maximum difference between these 6 tests. So this is in millimeters, so our maximum difference was sort of on the scale of 40 microns. And on that scale, we're probably down to the measurement accuracy. So it was very, very accurate in deployment. And then also I tried to bridge the gap between the 2 extremes of the boundary conditions that I mentioned. So over here we have the partially restrained, so it coils nicely, but it's not very stiff. And then we've got the clamped, which is very stiff, but it doesn't coil very well. I developed this deploy mechanism that kind of sits in between those two extremes. So the single bolting point allows it to fold flatly, but then at the end of travel, it's allowed to form its radius, and then we've got this lever arm that comes in to try and recreate that clamped condition. And I'm going to stop there, and I'm going to say if there's any questions, and I've put my email up there as well, just in case anyone's got any questions they wish to ask.
Are there any questions for Jason? Okay. All right. Anyway, let's take care then. And I want to thank everyone for coming tonight. I was like, could everyone go to the front so we can take a photo? Oh, you guys can come as well. Everyone.
Yeah, just be careful with the edges.
Years of study.
Yeah. No, we shouldn't talk about this sometimes.
Go, squeeze in a bit.
Squeeze.
A little.
Tommy has to be a little bit shorter.
Okay. 3, 2, 1. Okay.
I don't know why I'm smiling because I've got a mask on.
Thank you everyone.
Thank you, everyone.
Wait, so we do have food. Yeah, okay, well, okay, so, right, so we're gonna close the meeting. So everyone, hold on, sorry. Yeah, so for everyone online, so we're gonna close the meeting now. And I'll leave that for Carl to handle that. Otherwise, thank you everyone for coming tonight. We will put it up online, and if any of the speakers are not comfortable with that, please let me know. But otherwise, yeah, thank you for coming, everyone.
Thank you.